That's the real. It's not that they're all separate. They are all interacting. And then when you measure it, they become separate.
Yeah. So in some sense, you really have to regard them as all being there. And this is. I mean, if we actually knew how to compute path integrals, right? This is something where there might be a vast simplification. There was a big flurry of activity about twistor string a decade or two ago, and what twistor string enabled people to do was to, for certain path integrals, in perturbation theory, you would have this. This horrendous path integral, fourth order corrections that, might take a supercomputer 3 or 4 months to work out all the integrals and come up with your prediction. But using twistor string, you're able to simplify the path integral in such a way that you reduce it to 20 ordinary integrals and can do it in an afternoon. Right? So, with that kind of a simplification, you might get that kind of an insight into what is actually interacting. There might be a whole other way to see what's going on that is much simpler.
Right. Amplitude-hedron.
Who?
Amplitude-hedron.
Amplitude-hedron.
The positive Grassmannian by Arkani Ahmed. He's shown how you can take Feynman diagrams that are 100 pages and reinterpret it as the volume of a certain surface.
Oh, okay.
Or a volume of some kind.
All right. Oh, that's nice.
And it's done like that.
Yeah.
It's purely geometric.
Yeah.
No space-time.
Right.
Nothing.
Right. Yeah.
One more remark.
Yeah.
Someday, if you could teach 2 classes, Bohmian quantum mechanics, okay, and the many worlds interpretation by Everett, we get into all that.
Yeah.
Fun.
Yeah. Those are fun. The key thing for me in interpretations like that is that the question I would ask is whether they suggest new questions to ask. Whether they either radically simplify some calculations. I mean, that's always a plus. Or if they suggest new experiments and new possible ways of thinking about things that really give you more power in solving problems. My feeling about many worlds is it's calculationally impossible. You could formulate what to compute with those, but you would end up doing ordinary quantum mechanics calculations in the end, of course. If not, it would probably be wrong. But it has never seemed to me like that was going to lead to any new predictions or any simplifications in existing problems, existing calculations.
But the many worlds interpretation is so great because there's a universe where Trump is not president.
Hopefully lots of them.
Sorry if I offended.
Oh no. You've just catapulted us all into All right. Okay. Yes. On that note, let me recap what is on the video from last time. But I'm not going to go through it all. What I did was I dodged the description of Casimir operators. Let's look at the Poincare group a minute. And the algebra. But the Lie algebra, all right, we have operators, MAB, MCD, we've worked out this set of commutators a couple of times now. AD, minus, plus, This is anti-symmetrizing A, B, and CD. So start with this term and just add and subtract what you need to make sure it's anti-symmetric on these, and you get the right Lie algebra. Then you have MAB with a translation generator for the Poincare group. So the Poincare is just Lorentz plus translations. So you have these translation generators. So you're getting eta BC PA minus eta AC PB. Plus or minus that, depending on your definitions. And then the translations all commute with one another. So this is the Lie algebra of the Poincare group. Now, for any Lie algebra, you can ask for Casimir operators. And these are elements of the free algebra of the Lie algebra, modulo the Lie algebra itself. So what we can do is we can take products of generators of the Lie algebra, as many as we like. We can take linear combinations of those. Let's see here. Things like this. Modulo the commutation relations. So we can simplify some of these by rearrangements using the commutators. But other than that, this is the free algebra. This is the free algebra of like a Lie algebra. Okay, there are typically a 1, 2, 3, a few elements of this that commute with every element of the Lie algebra. And those are called Casimir operators. So these are elements of the Lie algebra, of the free algebra. That commute with all the generators. Okay, so there are two of these for the Poincare group. So for Poincare, we have p squared. Just contract it with the Minkowski metric. And it's not hard to see, all right, clearly that commutes with p. It's a scalar. It's going to commute with Lorentz transformation, so it'll commute with the m's. So it's pretty easy to see that an m with the p squared, whether we do it explicitly or not, this is going to give us a PC with MAB with PC plus MAB with PC, and I pull out a PC here. And you work this out, then that comes out to 0, too. Just use the Lie algebra, substitute this in there, it'll be 0. Right? I'll do it if you want to see it, but I'm probably not going to do the other one. I think, in fact, I give the other one as an exercise. But there's another one. What we define is we let WU be defined as, and let me get my normalization on this. Thanks, David. Where'd it go here? Yeah. 1/2 epsilon mu nu alpha beta p mu m alpha beta. Something like this. Then is it, I believe, W squared is a Casimir operator. And that takes a bit of work to show, so I give it as an exercise. It's, try to be a little clever in your arrangements of things, and it's not so bad. But the real question is, what are these? because these are invariants that characterize representations of the Poincare group. Anything that the Poincare group acts on, you can apply these operators and diagonalize them, come up with eigenstates of these operators, and everybody's going to agree on those, no matter what their origin or Lorentz frame. Right? So this is the kind of thing we want to make predictions. This is the kind of thing we want to label particle states. What are they? Well, I think you know what p squared is. What is it? It's the 4 momentum squared, right? What is it?
Energy.
Yeah, p squared is, depending on your signature, I guess we're looking at m squared c to the 4th. It's the mass. So one of these Casimirs is telling us the mass of states.
And then don't you get out the momentum to the relativistic energy to it?
That depends on your Lorentz frame.
Okay.
That's not invariant.
Well, you said 4 momentum.
Yeah, I mean p mu is the 4 momentum. Yeah, or
Yeah.
PA. Right. Really, you could write it as a translation generator, right? Like that in a function representation. But think of it as the momentum. But now, what is this w squared? So what I want to do is look at w. First, I want to boost p mu to a unit time-like vector. Unit time-like vector. Then, in that frame of reference, I can write w as epsilon. All right. So mu 0 alpha beta m alpha beta. Well, this is clearly orthogonal to that time-like direction. This is a space-like vector. P mu w mu is 0. So in this frame, I can write it as wi, and this is going to be, let's make it minus epsilon I jk m jk. Now, these are the spatial Lorentz generators. This is minus a half epsilon 0 I jk. I can write this as epsilon I, jk m times generators of the three-dimensional rotation group. So now, so I get some Kronecker ij here with some normalization. This is proportional to ji. So that means that the usual three-dimensional angular momentum squared is a Casimir operator for the Poincare group. Basically, this measures the total spin, total angular momentum. So what we're going to do is classify all of our particle states by mass and spin. So a particle, and this is back to your friend Wigner, a particle is a representation of the Poincare group, characterized by mass and spin. So what I did last time, in preparation to make this talk short, was to find all representations of the rotation operators in 3 dimensions, all representations of the rotation group. And what characterizes the rotation group is the Lie algebra. So from here, we could turn to a study of the Lie algebra of rotations, which, regardless of representation, is up to some constant, this. Okay, now, we know that the Pauli matrices satisfy this kind of a relationship. There's a 2i here, but who cares? ijk, sigma k. We can define, if we define tau to be minus I over 2 times the Pauli matrices, then the tau satisfy exactly this one. What we set out to do last Wednesday was to find all representations. Here are two. You know, if these are real antisymmetric 3x3 matrices, we know that we can find such matrices that satisfy that relationship. We do that, that generates SO3 if we exponentiate it, right? We know we get SU2 if we exponentiate these. These act on a two-dimensional vector space. These act on a three-dimensional vector space. Representation theory asks the question, you know, what are all the vector spaces I can let this act on? And what we showed last time is that there's exactly one of every dimension. So there's a representation of the rotation group of each integer dimension, 0, 1, 2, 3, and so on. Something with no spin, you know, is a one-dimensional representation. Spin 1/2, we get a two-dimensional representation. And in general, we constructed states labeled by, this is not mass in this case, but the eigenvalue of Jz. So we found states like these familiar ones from quantum mechanics, where J squared acts to give J plus 1, H bar squared, Jm. Now these kets are vectors, they form a vector space, and the dimension of the space is 2J plus 1 dimensional vector space. And the values of J that are possible we proved to be 0, 1/2, 1, and so on, 3/2, any half integer. Okay, so these are all the vector spaces that the angular momentum operators, the rotation operators, can act on. And these are, in fact, what are called irreducible representations. And to help you understand what an irreducible representation is, let's look at a reducible one and reduce it. So let's let M be a matrix. All right. I can write that as its trace, and let's see, so if the trace of this equals the trace of that, then I better put a third here. And then I can add an antisymmetric part. So I can write 1/2 Mij minus Mji. And if I do a rotation of this matrix, I get some other matrix. Well, if I do a rotation of the Kronecker, I get the Kronecker. If I do a rotation of an antisymmetric matrix, it stays antisymmetric. Then I have the remaining part, the symmetric part, the symmetric traceless part, minus, okay, I need trace M delta Ij with something here. I want this to be traceless, so I'm going to get trace M here times 2 minus 3 lambda trace M, and I want that to be 0, so I better choose lambda to be 2/3. So let's let lambda be 2/3, and that's the traceless symmetric part of this matrix. And you can see these all, you know, half of that is going to cancel that. I add these two together, and the Ji part cancels, and I'm left with Mij. This is an anomalous identity, right? But what we can also see from this is that if I apply a rotation matrix on each index, I and j, rotated as a rank 2 tensor, these are going to map to these will map to these, and those will map to those. Those symmetries and tracelessness will be preserved by the rotation. Those are the irreducible parts of a rank 2 tensor under SO3. Well, these are the irreducible parts. And in fact, if you look at the dimensions of these, this is a one-dimensional space, this is a three-dimensional space, this is a five-dimensional space, right? This is 2j plus 1 for j equal to 0, 1, and 2. Now we're missing the half integer pieces. You really need some more general notation to see those. But this is a decomposition of this general M into a combination of, a one-dimensional space, j equals 0 and j equal 1 and j equal 2.
Is this the same thing we do when we, for example, we say in a standard model, we want representations that obey all the symmetries at the same time. Mm-hmm. So we want something that is SO1, 3 cross SU3 cross SU2 cross U1. But that particle or that particular representation is different for each group. So are those differences, do they have to do with the reduction of this into different representations of the same thing? So for example, if I want to represent something in SU2, I represent it with a particular kind of matrix. If I want to represent it in U1, I'll make it a complex number. If I want to represent it in SU3, I make it a 3-dimensional matrix. But I'm still describing the same thing, but in different representations. So all those representations, are they from reducing that same thing to reducible representations like this, or?
That felt like several questions.
Okay.
No, that's okay. Let me kind of address a few things. So what we did last time was we found all representations possible for the rotation group, that follow from this Lie algebra. And, it tells us, okay, we should expect spin. So, any object that transforms linearly under the rotation group can be decomposed into these irreducible representations. So there's that. Now, what we do here, you refer to the standard model and all those symmetries. In fact, this list of Poincare Casimirs is just part of the story because there are other symmetries in nature, right? And there's SU3, there's SU2. We have the electroweak theory. These are additional symmetries, and those have their own Casimirs. So in fact, a full particle state, we're going to put more labels than just mass and spin.
Okay.
We're going to put color, we're going to put isospin.
I see.
We will add these other.
So it can go for any group and any representation.
Yeah, so you look at the Lie group, you find its Casimir operators, these are largely known, at least for familiar groups. So you then classify states by those Casimirs, and you may even add other labels as we do for spin, because even though not all rotations are going to have the same M, this indexes the vector space that this spans. This is a 2j plus 1-dimensional vector space where the M is run from minus j to plus j. Those label the 2j plus 1 different vectors, basis vectors for that space. Okay, but this is our toehold on how to label particles, how to classify particles. And our next endeavor is to systematically step through and quantize free spin 0 particle, quantize free spin 1/2 particle, quantize free spin 1 particle. Well, we'll look at particles that satisfy the Klein-Gordon, the Dirac, and the Maxwell equations, respectively. We'll look at these in vacuum with an idea to the real problem of quantum field theory is to characterize their interactions with one another. That'll take us to QED and, into next semester or something. Okay, so that, I think, brings us to chapter 4. And how much have we talked about? Are there any questions on classification? We're good there. Okay. How much have we talked about functional derivatives? Have we talked about functional derivatives?
We did in passing when we
related
were
to
talking
just
about Hamiltonian mechanics.
Yeah, that you just need to. Okay, so let's take a little digression and talk about the functional derivative. When we vary an action, let me just erase the whole board here. When we vary an action, we set the variation to 0.
Yeah.
And there's a generalization of all that where what we're doing is setting the first functional derivative of the action to 0. And that's what we want to get to here. So it's okay to define the variation of the action as the action at, say, x plus some small h minus s of x,
Yeah.
at linear order in h. But it's sometimes nice to have a little bit more formal definition of this thing. The idea of functional differentiation actually allows us to iterate the procedure and continue taking higher and higher functional derivatives. So this vanishing action is is just the tip of the iceberg when it comes to working with functionals. So what we get when we do this, right? We vary an action and, well, we go through a series of steps, but basically we end up with the Euler-Lagrange equation here. We end up with, say, d dt dl dx dot minus dl dx.
Yeah.
Del x. We work through, and I think we all know how to get that by varying integral of L dt. But what we would like is to think of this del s as del s del x del x, so that this thing is the functional derivative.
Okay.
So the Euler-Lagrange equation as the first functional derivative of the action. And we can do this with a few semi-formal steps. If we write out something like this, a la chain rule. So we think of del s. Now wait, let me see how I want to write this. Okay, yeah. So we think of this as a functional derivative times del x, and then inside the action, let's think of this as x of t. But here, all right. So we have our Euler-Lagrange expression. But then here we have del x of, let's let this integral be over t prime. So this is x of t prime del x of t del x. And we can get out the thing we want if somehow we could replace this by a Dirac delta function. Or, even, let's see, delta of t minus t prime. Right? If we do that, if this becomes a delta function, then we just do the integral and then we get the Euler-Lagrange equation. We get the Euler-Lagrange expression. It's not an equation unless we set it to 0. So the question is, all right, so can we do that? Well, what we got back here, when we did this procedure, what was sitting here was h. And we thought of h as a small function. There's nothing small about a delta function, right? It diverges. You can't think of that as some infinitesimal perturbation of a path. So how do we get from one of these things to the other? And while simply thinking of this functional derivation as a Dirac delta function works to get out the thing we want, I summarize some formal steps that let us actually get there. So, what is a Dirac delta function? Can anybody define it?
It's a limit, right?
Yeah. It's the limit of a sequence of functions.
Uh,
Well, all right, so delta of, let's say, t minus t prime is a limit as n goes to, let's say, infinity, of a series of ordinary functions hn of t minus t prime, where, let's see, the integral, the limit as n goes to infinity of the integral of hn t minus t prime times any test function f of t prime dt is equal to f of t. Right, and it works to take this to be a sequence of narrower and narrower and taller Gaussians. That's one possibility for such a sequence of functions. But these functions should be well behaved. These should be, C infinity functions or something nice. They don't. I mean, they could be square boxes or something, but they should be reasonably defined functions. A test function is C infinite and compact support. You can differentiate these as much as you like, and they vanish outside of some compact region. Right? That makes integration by parts very reliable. So if you have derivatives of these things, then you can integrate over here, and everything will behave nicely and vanish at your boundaries. Okay, so as I said, one example of this would be, say, normalized Gaussians. So if you take a series of Gaussians where the integral of e to the minus x prime squared over 2 sigma sub n, with some a sub n here, the x prime is 1. So you choose these coefficients and those standard deviations so that these are 1. And what you want is, let's let sigma n be something like, should that be sigma squared here probably? Let's let sigma n be just 1 over n. Okay, and then this is something like 1 over root 2 pi sigma squared or something, I think. I forget, but something like that. We know how to integrate Gaussian things over the real line. So this is a sequence of functions that has this property. Well, an integral past any of these, as sigma becomes large enough, becomes negligible outside a certain region. So you can make it small enough, you can approximate the integral and show that in the limit, this actually occurs, that you're really picking out the value of this at the peak of that Gaussian. And you can work through some examples that do this. So knowing this, and if you want, I'll give you some practice with defining delta functions in different ways, but knowing that this is how you define it gives you a clue as to how to rigorously define this so that you get a delta function out. Because each of these h of t's could be a deformation of your path. So what I want to define is x sub n equal to my path plus some epsilon h sub n of t and t prime. This is x sub t. Something like this. Let me check my notes to make sure I'm not forgetting some little detail here, but yeah, this is what we want. Then calculate, find s at x n of t. There's your action. So you're going to integrate your Lagrangian and xn dot maybe t. And now, let's see. So, well, t or t prime. Let me just call one of these t naught and write this as the function of t. Then what we can do is expand this out. Right? So this is L of x plus epsilon hn, x dot plus epsilon hn dot, possibly t. So if I look at the ordinary derivative of s with respect to epsilon, what I'm going to get is the partial of L with respect to x times, by chain rule, the derivative of this with respect to epsilon is going to be my hn. Then I get the partial of L with respect to x dot, and I'm going to get an h dot sub n. And all this integrated dt. I do my ordinary integration by parts here, and I'm going to get my Euler-Lagrange equation, dl dx dot. But this is x sub n. Well, this is with respect. This derivative is with respect to this variable. This is with respect to this variable, whatever epsilon or h are. So I'll just call it dl dx, referring to first position, plus dl dx times h sub n at t and t naught dt. And now I take a limit. So I take the limit as n goes to infinity of this derivative, the epsilon, and so I'm taking the limit of that, and the only independence now, there's still independence in here. How can I get rid of that? I'm going to evaluate this at epsilon equals 0. That kills off the higher terms, and that kills off this dependence in this expression. So the only h that's left over is the linear term. So this is at epsilon equals 0. And now I take that limit, and it's the Euler-Lagrange equation times delta of t minus t naught dt. I do the integral, and I get out my functional derivative of s. Voila. So I define the functional derivative as the limit as n goes to infinity of the derivative of the action with respect to epsilon evaluated at epsilon equals 0.
So that's the reason that negative comes in at the end of there.
But here, I integrated by parts and got a minus sign.
Yeah.
I mean, I could have taken this to be minus, or I could have written this the other way around or
Yeah,
something.
I see.
But yeah.
It was just the opposite.
Oh,
there.
I cheated up here. It's probably minuses.
Oh. Couldn't you just do that whole thing, but just say cancel the delta x on both sides there?
Just cancel a function out of an integral? No.
Yeah, of course.
Yeah, no, you want a careful definition that really works, and this actually does it. So formally, we can define the functional derivative of s with respect to x as the limit of an ordinary derivative evaluated at epsilon. Now, let me add, you really do need to go to a little bit of detail like this, because back here, way at the beginning, suppose I had tried to say, I just want to let del s del x be s of x plus h minus s of x over this function h of t, and the limit as h of t goes to 0. Like an ordinary derivative. What's wrong with that? Why can't I just define it like an ordinary derivative?
Because it's a functional, right?
Well, it is a functional, but okay, so the difference of two functionals, okay, fine, divided by some function in the limit as that goes to 0. What's the problem here?
The function is not a functional?
The function can be 0.
Oh.
Yeah.
Maybe it's, some small thing some places, but it can be 0 as many times as you like on that interval.
Yeah.
So, you're just dividing by 0 all over the place.
Yeah.
So this really doesn't work. No.
Yeah.
Okay. So now we know if we have to take a functional derivative, how we do it. Notice that taking the first functional derivative is just, it's taking partials of the action and really doesn't look very different than what we usually do when we vary an action. So unless we get hung up in varying some action, we don't have to resort to all of this. So, Klein-Gordon scalar field.
Yeah.
Spin 0. Mass m. All right. Let's start to move towards some quantization. Slowly. Okay. The joyful thing is here that I think we have actually accomplished the preliminaries. We've defined enough things that we can actually start to quantize some fields. So let's start with the Klein-Gordon action. And then let's say I have to think which sign I want here. What I have here is minus m squared, and since I've worked that out fairly recently, let's just hope that's right. Before x. So now here the Lagrangian is actually the integral of a Lagrange density, d3x. And now let's, so the Lagrangian is 1/2 integral all this same stuff, but d3x. And then s is the integral of L dt. But these together make a full space-time integral over some region of space-time. So then, let's take the functional derivative. So del s del phi of x. And so let's see, what are we going to get? Let's hang on. Let me call this y. And when I write simply x or y, x really means x alpha, y really means y alpha. I'm referring to all four space-time coordinates here, just writing an x or a y to indicate all four coordinates. Then what I want is a half del phi of y of this action, d mu phi of x, d mu phi of x minus m squared phi of x squared d4x. So I bring this in, right, integration over x, differentiation with respect to phi of y. So we're not in any conflict bringing this inside. We're going to get to d mu phi of x times d mu del phi of x del phi of y. Then here minus m squared times 2 phi of x del phi of x del phi of y d4x. Okay, so what I want to do is the short way, where we went through all that. What basically happens, all those HNs turn into a delta function in the limit. So I'm just going to go ahead and write this as del 4 of x alpha minus y alpha. Right? That's the functional derivative of a function with respect to itself. And here, however, I do have to integrate by parts. So canceling the factors of 2 with the half, and integrating by parts and throwing out the boundary term, because I'm not going to, I suppose that this functional derivative vanishes on the boundary. Then we're going to have minus d mu phi of x plus m squared phi of x del 4 of x minus y d4x. And so the functional derivative with respect to phi y is then minus box phi. The delta changes the x to a y. So now this is y, the box is with respect to y, plus m squared phi of y. And if we set that to 0, we have our Klein-Gordon equation. Okay.
So when we're taking this functional derivative here, is like x a function of y then? Because those del phi x over del phi y turns into the Dirac delta, and then the Dirac delta goes away.
X and y are, think of them as just parameters, like t in our usual action.
Mhm.
We're really looking at phi at some point, phi at some other point. And those are independent
Okay.
unless x equals y.
Okay.
I know.
Yeah. So you vary it, you go through the variation with respect to x, but then like at the last thing you just take it at a point. Yeah.
That's right, yeah. So we're going to do the
I see.
integral. We've got, this vanishes except at that point, and at that point, boom.
Yeah.
So we get to pull it out of the integral. So that gives us the first functional derivative. And let's see, so then as exercises, I ask you to find the field equation for a complex scalar field, a Dirac field, and Maxwell equations. But let me back up and
Does it become
write those actions for you.
Does it become much different for the complex scalar field?
No,
Yeah.
it's very similar. You get two Klein-Gordon equations, right? You vary them independently.
Mm-hmm.
Right?
Oh, because
when the field is
vary
complex,
x and vary y in x plus I
yeah.
y.
When you have a complex field, you can vary it and its conjugate independently.
Oh, okay. So you take
Right,
the
and
conjugate.
I mean, you could write it as real and imaginary parts, vary those two parts separately,
Yeah.
but you can show that you get the same thing as if you varied
I
it
see.
and its complex conjugate
Okay.
separately.
Very cool.
So we're going to look at a number of different cases. The complex scalar field. Anybody know why we're going to take time to look at this one?
Because quantum mechanics has complex numbers in it.
Well,
Electromagnetism?
yes,
U1?
electromagnetism. It has U1 invariance, whereas this Klein-Gordon does not.
Oh.
And we're going to want to look at couplings to electromagnetism. We're going to want to assess the charge of various fields. We'll have some kind of charge operator. And yes, that's right. So the complex scalar field, you don't need the half anymore. But it's just d mu of phi conjugate. That's supposed to be a conjugate here. D mu phi minus m squared phi conjugate phi.
I see.
Right, so you vary phi conjugate, integrate by parts, you're going to get the same thing. You vary phi, you get the Klein-Gordon. So then we have the Dirac equation. This is a spin 1/2 representation. This is a spin 0 representation. Then the Dirac action is, right, I'll write it the short way, id slash minus m, psi bar here, psi there, d4 x. Let me also write it out in grisly detail. This is psi dagger times gamma 0 times I gamma mu partial mu minus m psi d4x. And again, we can vary psi and psi dagger or psi bar independently here. If I vary psi bar, boom, I've got the Dirac equation.
And of course you don't have to vary gamma.
No, gamma's just constant matrices,
Yeah.
4 constant matrices. We have plenty of representations for gamma. Then we have electromagnetism, E&M or Maxwell fields. Now, for Maxwell, we have a quarter F mu nu d4x. This is the free Maxwell field.
Okay.
And that's the one we're really going to look at. You may be used to looking at a quarter F mu squared, F mu plus J mu A mu. Right. This is the Maxwell field with a phenomenological source current J mu.
Yeah.
We don't play with phenomenological currents in quantum field theory. Right? This is going to come from gauge theory. So we don't add a term like this. What we do is we gauge the U1 symmetry of the Dirac or the charged Klein-Gordon field, and the covariant derivative will automatically give us this term, where this is the conserved Noether current of these fields.
Okay.
Right? Neat, huh?
Yeah. Just take a covariant derivative.
It's very nice.
effect.
It suddenly gives you like a feeling of like a frisson. It's like, oh, this is fundamental in a different kind of way.
Yeah, kind of spooky.
So we have this, but this isn't what we use. What we use is a free Maxwell field, free Dirac field, free charged scalar if we like, but then we require the global symmetries of these to be made local and to agree with the gauge theory. And that results, right, if this derivative becomes a covariant derivative, which looks like a derivative plus some gauge field, then what you've introduced is something like psi bar a slash, because there's a gamma matrix here, psi, and that gives you your conserved current. So when you vary A, okay, you get Maxwell diversions of F here, but you also vary it over in the Dirac, and that's going to pull out this current. So the current, right? This is A mu with psi bar gamma mu psi. This becomes your fundamental J for the Dirac field. It's weird that it has no time derivatives, but the Dirac equation is weird in a number of ways, and we'll encounter most of them. Okay, then there is such a thing in the literature as what's called a Kalb-Ramond field. I'm sorry, no, that's a different field. A Rorita-Schwinger field is a spin 3 house field. It's the superpartner, the fermionic superpartner of the graviton in supergravity theories. We won't look at that anytime soon, but then of course we do have the gravitational action, which is the Einstein-Hilbert action, and this is a spin 2 field. G mu nu, you think of as the fundamental potential here. This is actually a two-step thing because this depends on second derivatives of that, whereas these fields depend on, this F depends on first derivatives of the potential. So there are things that are different about gravity and various ways of sort of rethinking gravity to try to patch that up. But so, okay.
Question?
Yes, yeah, sure.
What about the gauge symmetry for gravity? What does that give you?
Right. It is simplest if you want to write gravity as a gauge theory to restrict the symmetry, or restrict the basis for your tangent or cotangent planes to orthonormal frames. You can choose an orthonormal basis for any vector space. So instead of taking an arbitrary coordinate basis, ddx mu, for your vector fields, so some vector field is often written this way. Instead of that's a coordinate basis, you can choose an orthonormal basis, VA, some EA. And in an orthonormal basis, the symmetry is Lorentz rather than general linear. So, coordinates, yeah, you can do arbitrary general linear coordinate transformations, but allowing yourself to do a transformation between infinitesimally separated orthonormal frames is just as good, right? There's actually a theorem that, if you know this, you know that, and vice versa. So first thing, you work with orthonormal frames. I like to work with differential forms, so I work in the cotangent space. But whichever way you work, now you gauge the local Lorentz symmetry, global Lorentz symmetry to be local. Maybe you have some field that's this field is globally Lorentz covariant. You can write these derivatives in some orthonormal frame, and then you change this to a local Lorentz invariant theory, and then, as you do in any gauge theory, you add the field strength of the connection of the covariant derivative. The field strength of a connection is invariably sort of d of the connection plus some structure constants with a quadratic thing, right? So this comes from the Maurer-Cartan equation, which I won't go into here, but the let's I don't want that. No, that's plus. This is the field strength for any symmetry we like. If I have a Lie group with structure constant C, then there is a covariant tensor field strength of this form. Well, this is the form that you get for the Riemann curvature 2 form from the orthonormal connection, called the spin connection, like this. So it takes the same form. So R is the field strength associated with this, but it suffices then to take an action linear in that to get the Einstein field equation.
So the current is energy momentum tensor.
Yeah, that's right. If you vary any of these field actions with respect to the metric, you will get the energy momentum tensor.
Oh.
Necessarily in the symmetric form. So that source will automatically come out from the coupling. These will become covariant derivatives. You vary the metric or connection, and you're going to start picking up stuff here. And those will be the right source.
And then you get
The variation of the field action for any field you reasonably write down is the stress energy tensor for that field.
So then if you vary the metric on the E and M action there, you'll get out F mu nu.
No, let's just do it. Yeah. So, yeah, let's write the
So how is this
action.
quantization?
But when we make it, sorry, what's the question?
How is it quantization?
We haven't quantized anything yet.
Okay.
Yeah, we're going to put hats on everything.
Okay.
Then it's quantized.
Your brain's too fast.
Okay.
Yeah,
I just wanted to be sure I'm not missing some fundamental concept.
No. We haven't quantized anything yet, Dave.
Okay. So we're just doing gauge theory, pure. Okay, cool.
So here we are in flat space.
Yeah.
But if we go to curved space, we generalize this, and it turns out that the general coordinate generalization of these things, of a field action, I'm going to put the metrics in explicitly,
Okay.
and then I have to put in this is basically putting in the Jacobian, and now I have a general coordinate covariant volume element. So now if I vary the metric here, I'm going to get two terms where I vary this. They're going to be the same. So I'm going to have a half F mu nu F alpha beta G mu nu del G nu beta. And then I have to vary this determinant and see my GR notes for how to do that. But the result is, let's see, minus a half. Well, let's see. Let's just leave the quarter out here, so I get a 2 here.
Right.
Then here I get minus a half G rho sigma del G rho sigma times, this is just F squared, times the root of G. There, root of G comes out, d4x. And so now, if I make this, let's see, yeah, let's make nu beta, let's make that a rho sigma. Nu beta becomes a rho sigma. Then what I have is, up to an overall multiple. Let's see, so let's put in a half. Then we have F mu rho, F mu rho F mu sigma minus 1/4 G rho sigma F mu nu F mu nu root minus G d4x. This is the stress energy tensor for electromagnetism.
So that explains the deflection of light around the sun.
Well,
You could use that kind of equation, right?
well, you don't need the coupling to electromagnetism to study that. All you need is the geodesics of the geometry.
So that's interaction of light with gravity.
All free elemental particles, spin-free particles, follow geodesics. All right, in the absence of other couplings. So you don't need this. All you need is, say, the Schwarzschild solution, and you look at the null geodesics.
Or the light-like or time-like.
Yeah, light-like geodesics. Those are the paths you expect light to follow. Now, if you do put in this term, then calculate, well, what is the stress energy tensor for that single photon that just flew past the sun? This is going to be extremely small. It will have an effect on the geometry, but negligible compared to, say, the sun. Right? So this is going to put the effect of some electromagnetic field on the geometry. And there are some solutions. There are some electrovac solutions.
So light bends space.
Yeah, it does. But
Because it's energy.
it's energy, so it does bend space, yes. But the bending here compared to the bending of a vacuum solution to a spherically symmetric body,
Well, ask Kip Thorne about that. See what
Oh, okay. Yeah, well, yeah, I suppose at LIGO they might be interested in the gravitational effects on the light. I mean, they have to pay attention to extremely small quantities there. Yeah. You ever heard of squeezed light?
Vaguely.
Yeah, in a regular laser beam, the uncertainty in position and momentum in dimensionless units are the same. But you can pass the coherent light through some crystals or something, and you can alter that relationship so that it's more certain in position, less certain in momentum, or vice versa. That's called squeezed light. And it turns out that a lot of media can produce squeezed light, but gravity does too. If you pass a coherent beam through a strong gravitational field,
Talking about the gravitational birefringence.
I don't know that that's the same effect.
Oh.
I mean, there are lots of effects of gravity on light. This is squeezing. Squeezed light it can be produced by a gravitational field.
Yeah.
And it's a fairly small effect.
Yeah.
I don't know. I don't know if it could be measured at LIGO or not. It's not so far from the capability of LIGO to measure that.
Yeah, the last Nobel Prize was about light also.
Yeah.
One, the lady won.
I bet half the Nobel Prizes are about light. Yeah. Or there have been at least 3 Nobel Prizes awarded for studying spin half systems. Just understanding things about spin on half. Yeah, and light is inexhaustible. The more you understand about light, the better. So,
What is a photon, right?
Mm-hmm.
Yeah, right. So, yeah, we'll get there soon.
No, I was just listening to how he defined a particle as a
Representation of the
Poincare representation.
Yeah.
I was like,
I'm still mystified by that. It's like that has been turning and turning
Yeah,
the
now-
whole time.
Yeah, now we probably have to say it's a representation of, the Poincare cross SU3 cross SU2 cross
So
U1 or something. And, yeah, that gets complicated. Let's see. Let's see. It's quarter up. Should I find the conjugate momentum, or do you
there's
wanna-
one cow outside already.
There's the
Several.
cows. The cows are
One.
all right.
Several.
Okay.
Yes.
all
Oh,
right.
really several?
Yeah. Let's start there because the next steps really starts with the quantization.
Okay. So we can prepare for quantization. Put on our hats.
Right?
So the point is, you can do that with all of those because all of them had D4X.
Yeah.
So they all have.
Yeah. If you have a field action, quite generally, putting in a root minus g, so that the volume element transforms right. This basically transforms with the Jacobian,
Yeah.
and that's what you need for the D4X.
So that's always there. That's the background.
You put this in, and now you can do general coordinate transformations. You need to make all the derivatives covariant. Now, with an antisymmetric field like this, the connection drops out. So this doesn't change. But if you had something like the Klein-Gordon field up there, those derivatives would have to become covariant derivatives. But this is what you do with any theory. You don't usually have to worry about the volume element, but you make all the derivatives covariant derivatives with respect to whatever transformations you're talking about, and that will give you locally covariant equations.
Okay, that's plenty.
Davis, we're having a Nigerian Independence Party in Salt Lake this weekend, so you should come.
Oh, what time? When
They start in the evening, like 8 p.m. on Saturday.
Saturday.
Yeah.
Okay, cool. You guys are making food?
Of course, there's a lot of.
Yeah.
You can
Okay.
come with your-
Okay.
you should come with
So there's good reason to show up.
Oh.
Yeah.
That is a serious draw.
Oh yeah, Professor.